Hello, everyone. Today we're going to look at nuclear fusion, shaping the future of clean energy. Okay, let's start with introduction. So, nuclear fusion is often called the energy of the future, and it has been for the last 50 years. So, the idea is pretty simple. Copy the sun, put its power in a machine, and solve the world's energy problems. The reality is, of course, is a bit trickier because you can't put the sun on a world. In this presentation, we'll look at what fusion actually is, how scientists are trying to make it work, the different machines built around the world, and why this race to bottle a star is both frustrating and fascinating. Let's start with how nuclear fusion actually works. So, easy peasy. Inside the sun, which is super hot and super heavy, the hydrogen atoms squeeze so tightly that they fuse into helium. Sounds cool, right? The heat is extreme and the gravity extreme. That equals so much pressure that you actually fuse to one another. Now, because of Einstein, well, not because of Einstein, but the equation he found out, E equals mc times square, pro- releases huge proves that it releases huge amounts of energy, and it shows in the form of light and heat. That's what makes the sun shine so brightly, and it's so hot. Thank you, nuclear fusion, or not thank you, because I hate being in the sun's rays. Anyways, on Earth, we try to copy this by using powerful magnets or lasers to create the same extreme conditions inside a machine. We still have a lot of problems, though. So, types of nuclear fusion reactors. I know three different fusion reactors. The first one is a stellarator, which is a donut shaped machine that uses powerful magnetic shields to confine superhot plasma. Another is the stellarator, a twisted version of the tokamak designed for continuous, more stable operation. And a very different method is inertial confinement, where lasers or particle beams compress tiny fuel pellets in short, intense bursts. But it's pretty short and intense bursts. Anyways, let's start with stellarator because I'm kind of biased when it comes to Germany. Anyways, the stellarator uses twisted magnetic coils to keep plasma stable for long periods. It's a bit like the tokamak, but more twisted. Germany's Waldenstein 7X set a world record by sustaining plasma for 8 minutes at 50 million Celsius, proving accelerators can run continuously. And yeah, a big step toward real fusion power. And yeah, Germany's cool. Whatever. Number two would be tokamak. The tokamak is a donut-shaped reactor that uses powerful magnetic fields to confine plasma. France's ITER project aims to produce 10 times more energy than it consumes in the 2030s. Keep Germany. While China East's artificial sun has already held plasma at 158 million Celsius for 1,056 seconds, which is really cool. Great for China. Next is laser fusion. Laser fusion, or inertial confinement, uses powerful lasers to compress tiny fuel pellets until they ignite. In the US, the National Ignition Facility, NIF, made history in 2022 by achieving net energy gain for the first time, proving fusion ignition is possible in short bursts. But it doesn't compare anywhere to mm, the tokamak or the stellarators. But that's just me being biased, I guess. It's not because I have a grudge against America. Definitely not. Okay, anyways, even though this sounds all happy and amazing, I already told you there are a lot of tricky things that you have to do to put a sun on Earth. Here are the risks and challenges. Though it doesn't carry the danger of meltdowns or large scale radioactive waste like nuclear plants, it does comes with a lot of problems. problems. Like, the biggest challenge is reaching and maintaining the extreme conditions for fusion. I mean, how can you put a sun on Earth using a machine? It's so developing materials that can survive intense neutron bombardment and building reactors at a cost and scale that make economic sense. Because you can't just throw money away and hope for the best, right? You have to think it through or it doesn't make economical sense if you just throw away millions or billions of dollars to. So, yeah. Tritium fuel also needs to be bred inside the reactor, which adds much more complexity. Here are the four main problems: achieving stable plasma confinement, high construction and research costs, of course, materials damage from neutron radiation, tritium fuel breeding and supply. All these are huge problems. Now let's talk about the heating methods in fusion, because I find this part really interesting. Fusion needs plasma hotter than 1 million Celsius because it needs to be 10 times hotter than the sun's core. To reach this, scientists use methods like ohmic heating, electric current, neutron beam injection, firing last atoms, radio waves, microwave heating, and laser compression. The most effective in large reactors today is a mix of neutron beams and radio waves, which also aren't too easy to complete. Now, let's talk about the future of nuclear fusion, because this is where my sci-fi brain kicks in. Because fusion is not just a theory or a myth or just just a theory anymore. It can actually turn to reality. ITER in France is set to begin plasma experiments in 2025, which is this year, by the way, and aims for full fusion power by the 2030s. China's East reactor is breaking records for temperature and confinement, while Germany's Waldenstein 7X continues testing steady-state plasma. If these milestones succeed, fusion power plants could be on the grid by the 2040s, which is 10 years later than the 2030s, but oh well. Good luck, France. So, let's conclude this presentation, yeah? Nuclear fusion is not science fiction anymore. It is one of the most promising paths toward clean and limitless energy. Just imagine, no need to be scared what will happen years in the future if the power plant will turn into a toxic wave that destroys the whole earth, like in some sci-fi movies. But that's not the point. It produces no greenhouse gases, leaves behind no long-lived waste, and carries no risk of meltdown. The challenges of plasma stability, material endurance, and fuel supply are real, like a pain in the ass real. But with projects like ITER, EAST, W7X, and NIF making steady progress, fusion is moving closer to becoming a practical power source. If successful, it could reshape our entire energy future, which is really good because the energy we are using is destroying the earth slowly and brutally. So, thank you for watching this video or presentation or whatever you want to call it, and this is made by Sylvania Templeman. Thank you for watching. Bye!